guys, how's it going? Like Karim said, I'm Ryan. So technically, I work for the Flare team, right? But officially, I work for the group that supports our kind of red teaming operation. I'll do all in the intro. But this talk is both sort of it's an interesting bug that we found, kind of spread across a bunch of drivers, right? But it's also sort of a walkthrough and a how-to about what is device driver exploitation, what does it involve, and then there's some gotchas that popped up with this primitive that we get with this bug specifically. So I'll go through the intro. I'll give you a quick little rundown of what being a device driver means on Windows, and then I'll talk about the bug, and then kind of the second half of the talk is sort of the nitty-gritty exploitation details, because a lot of talks are just like, oh, this is exploitable, so we're done, right? So I wanted to go through end to end to show you what like a fully functioning kind of exploit would look like. So, like I said, I'm Ryan. I work for the Flare team. If you guys aren't familiar, the Flare team and FireEye, we support sort of all of the reverse engineering efforts. So we're kind of like the whipping boy for the rest of the company. So if our products find something, we get the binaries. If our red team needs help, we help them. If there's an incident, we're kind of always supporting sort of whatever FireEye is doing at kind of like a low-level type thing. And then specifically, the offensive task force is relatively new, but its goal is kind of to support our red team. So we do a lot of payload development. We do a lot of debugging. We kind of are like the support line if something goes wrong on an engagement and they need some kind of help to get along. And then my Twitter's up there. I never tweet, but I think that's, you kind of have to have one, right? So that's what I am. So in terms of what this talk represents and why I'm giving it, right? Like usually when you hear about privilege escalation issues on Windows, it's in Win32K or AV drivers or something like that, right? But at the end of the day, there's a bunch of binaries kind of running in kernel space on Windows that are, maybe it's not obvious depending on what application you're using, but basically they're all over the place, right? And then I'll talk about this a little bit later, but we've seen sort of sophisticated actors use issues like what I'm going to describe here, where even if they already have quote unquote like higher access privileges, they've used these issues to kind of hop around and avoid security products or antivirus signatures or whatever, right? So in a lot of cases, if you've ever used like Process Explorer or Process Monitor, they have a driver component on their back end that kind of drives their GUI, right? So that's doing all the actual work. And the other place where you see these pop up is like I said, antivirus obviously has them. Anti-cheat stuff for games has them. So they're kind of all over the place. And like I said, some of the sort of exploitation stuff that you have to do if you find a bug is sort of unique to this kind of workflow, right? Like I already said, we've seen some of these be used in the wild. So what will normally happen from a kind of malicious perspective is you'll get infected with malware, and kind of the big boy actors will either search for these exploits, or we'll talk about it in a second, but you can drop and load these to exploit. And it's kind of a weird exposure thing, because basically if you have one of these issues present, then the way device drivers work on Windows and on most operating systems is once you compromise one of these, you're running code kind of at parity with the rest of the operating system. So anything that you can do with stuff like this kind of leads to total system compromise. Like one of the benefits is even if you say, oh, I'm on this box, I already have even administrator access, right? Because antivirus vendors and the security stuff on the operating system are all running at the same level as like these things that I'm talking about, you can use it to kind of avoid detection, right? And so we've seen it in some red team toolkits. I mean, it's already out there. Like if you've ever looked at how Mimikatz works, they have a driver that they package and ship that can do some of this, right? So, Mimikatz uses theirs specifically to make sure a subset of their functionality can work across kind of OS versions. But so yeah, I'll talk about kind of the interplay with this in a little bit once we talk about the bug, right? But before we can talk about the actual issues that we found, I'm going to give you a quick primer on like what it means to be a device driver on Windows. So usually drivers are tied to hardware, right? So like you have a mouse, a keyboard, or whatever, and they have a driver that's responsible for communicating back and forth with that peripheral. The kinds of drivers that we're going to talk about today are what's called like software drivers. And they're basically just binaries that kind of run in the background in ring 0. They're not responsible for handling hardware specifically, but they are responsible for doing, like I said, kind of basically like callbacks in the kernel to do stuff. So there's a bunch of reasons why you would do this. Like, for example, if you wanted to track process creation or you wanted to see what was going on, it's a lot easier to do that from a ring 0 perspective versus kind of writing a user out to pull everything or whatever. Now, when you have one of these issues, like I said, you're at parity with the operating system, but also the operating system doesn't buy you anything in terms of security, right? So if you write a device driver, you're also configuring who can talk to you, who has permissions to talk to you, and things like that. So that's kind of where some of this issue comes from, right? And then, like I said, you'll commonly see these both to do hardware support and also, if you think about like Process Explorer, since I already said there's a driver, Process Explorer doesn't need to do any communication with hardware, right? But it does do a bunch of stuff to like look at process memory or track creation. It does all this kind of sort of all of these events. It's all kind of filtered through this ring 0 callback kind of mechanism. So in terms of how do I communicate with a device driver, right? When you're on Windows, kind of the terminology is the lowest level communication mechanism is called an interrupt, an IO request packets or an ERP, right? And what happens is your driver gets installed, you start up, and you say, here's all the kinds of requests that I can handle. So there's kind of a pre-canned list of callbacks that you can provide. So Microsoft defines 28 different codes, and each code is generally tied to like an IO operation, right? So if I read a file or I write a file or I want to, we're going to talk specifically about the one that most of them use, but each function callback is basically a kernel function that's responsible for doing some kind of IO, right? So usually the one that we care about when we're talking about assessing device drivers is the one I have on the bottom of this list. So ERP-MJ device control is tied to a specific sort of API call in user land. But at the end of the day, I'll walk you through kind of the chain in a second, but you issue some kind of IO request and like the OS maps everything to a function pointer for you, and then it'll call some device driver somewhere in the kernel space for you. So this is kind of where we want to start fuzzing, unsurprisingly, right? This is how you communicate with these components. Like I said, most of the bugs you're going to find are going to be in the device control callback, but every once in a while, you can say like, there's other handlers. It kind of depends on the architecture, but for software drivers, it's usually kind of, there's only sort of one standard way to communicate with them. So we're going to focus on the ERP-MJ device control, and that's where we would want to look at our fuzzing, right? So again, I'm not going to go super deep into kind of the mechanics of how this works, but essentially, at a high level, in user mode, when you want to do some kind of I/O operation, right? So create file, read file, write file. What will happen is you'll issue this API call. The OS will do a bunch of stuff for you. And then there's all of these. I'm going to click through them really quick and just kind of talk through it at the end. There's all these kind of underlying objects that the operating system uses to kind of manage I/O operations, right? So if you're familiar with the Windows API, a lot of things that you do involve using handles, right, which are similar to kind of file descriptors on Linux, right? So each handle corresponds to a file object, and then each file object has stuff in it that basically says, like, when you're trying to do something on me, like, go call this guy, right? So the full chain is you get a handle to a file object, file objects have device objects, and then what we care about is kind of the driver object associated with it. So again, without going too deep, basically the driver object is like the thing that you define that says what all the functionality you have is, and then each device object is sort of like a particular instance of that. So it's similar to like if you've ever done C++, like the driver object would be like your class definition, and then you can have device objects that are corresponding implementations of it. But most of this you can usually ignore. It was just kind of a sort of a background thing. So what we really care about is this driver object, because the driver object is where those ERP codes that I was talking about a couple slides are defined. So what I have up here is kind of a dump of something that I was loading in WinDebug. And what you can see at the bottom, that sort of big list of stuff at the sort of lower half is all of those API calls or all of those function calls that correspond to different I/O operations that we talked about, right? So because Microsoft defines them, they're all in kind of a standard location, and you'll usually see something like this, where by default, when a driver gets loaded, it can't handle any I/O, and then sort of at startup, it'll say like, oh no, if you try to call read file on my handle, call this function. If you call device I/O control on my handle, you call this function, right? So for us, like I said, the one that we really care about is at the bottom there, so ERPMJ device control. That's the one that gets called. There's a special sort of API in userland called device I/O control, where you send kind of user-defined requests to an arbitrary device, right? So then, again, from a how do I assess these and what am I looking at kind of perspective, in kernel space, what usually happens is, because like I said, device I/O control is for developer-defined requests. So this part's not Microsoft standard or anything like that. But what will happen is, when the driver, is compiled or whatever, it'll say like, here's all the request codes that I can accept and I can run and to do different stuff. So what's shown on the slide here is kind of what it would usually look like when you're assessing one of these drivers, where there's basically just a big kind of switch statement, and it says, hey, command code 85F whatever, whatever, that corresponds, like I need to do this thing, right? So these are all developer defined, but again, when you're talking about fuzzing, these are important, because this is how you kind of tell the driver what to actually do, right? So this is kind of your first entry point when you talk about assessing these things. And then, like I said, the kind of only thing to remember is that they're all specific to a particular driver. So in terms of sort of device driver vulnerabilities, I think it's kind of an interesting class of software to look at, because even if you argue that like they're not super critical, device driver vendors and authors, they do a lot of dumb stuff. So you kind of have all of the usual bugs. You have Stack Overflows and integer issues and things like that. But you also have stuff where like just people that don't understand how security works or how the operating system works, just like turning security features on and off, or there was a pretty popular one that came out in like a game driver where they would just turn off kind of OS mitigation so they could run arbitrary functionality. So you kind of have this situation where, in addition to all of the usual stuff you would look at when you're doing exploitation, you also have like a bunch of dumb stuff that's just kind of cool. And we'll talk a little bit about kind of what I think the impact of this is. It's kind of like it'll be a soapbox moment for me, basically. But it's one of those things where it's very clear once you start assessing these that a lot of people do not understand sort of they understand what they're doing, but they don't understand why it's bad, kind of thing. So the specific bug we're going to talk about is unfiltered or unmitigated access to kind of a critical system resource, which, if you've been following the title of the talk, is this thing called model-specific registers. So I'm going to go over a little bit about what they are, what they're for, and then we're going to talk about what the actual exploitation mechanic looks like. So a model-specific register, or an MSR, are CPU, like basically they're special registers in different processors that do hardware maintenance stuff, right? So Intel kind of has their own set, AMD has their own set, and then most of them are agreed upon, but basically it's dependent on the vendor to say like, what can my processor support? Then when you're actually like using them and what are they for, like I said, they handle kind of low-level like hardware management, maintenance stuff. So if you've ever overclocked a processor, you can do some of that with an MSR. Temperature checks, you can do that with an MSR. Intel has like a branch tracing thing, so you can see, I ran this application, what kind of path did it take? That's all done with an MSR. And the one that we really care about is when you make a system call. So if you're not familiar, system calls are kind of the mechanism to go from user mode to kernel mode. The function responsible for handling that system call is also present in MSRs, right? So that's kind of that's why it's in red. That's what I'm going to talk about for most of this talk. Like that's where the issue is, right? Because like I said, they're kind of low-level sort of OS management stuff, right? Then if you have a kernel debugger attached or you're on a system, you can use these two commands I have at the bottom to read and write them. So you can kind of poke around and see what they are, and I'm going to show you what that looks like in a second. But just to make sure we're all on the same page, this is kind of, like I said, create file is like the most sort of common API call on Windows, right? So this staircase thing shows you sort of the life cycle of what happens when you actually say create file, read file, write file, whatever. And most of it we can ignore for this talk, but at a high level, basically, most of these APIs come from kernel 32, and then the implementation for them is in other sort of system DLLs that you probably won't call directly, right? So if I call create file A, it'll go from kernel 32 to kernel base, which is a sort of an implementation layer for a lot of these. And it'll keep going down, and it'll translate from ASCII to Unicode and do all this other stuff. But at the end of the day, the bottom of this slide says, ntdll dot nt create file. The exports in this DLL are only responsible for making system calls, basically. So if you look at the disassembly of one of these functions, which I'll show you in a second, basically all they do is say, like, you called nt create file, here's the system call number, off we go, right? So Windows is a little different from Linux because Windows system call numbers change pretty frequently, which Linux doesn't really do, right? So ntdll is kind of the thing you're supposed to use to actually do system calls, because that DLL will be updated and it'll have the right number in it for whatever version of Windows you're on. So like I mentioned on the last two slides, the transition from user space to kernel space is done via an MSR. The MSRs that I have listed on this slide are all responsible for handling system calls in sort of different scenarios, right? So we're really only going to talk about the top one, or sorry, the second one, I guess, so that 82 MSR, because that's kind of the default one. But the other MSRs that I have listed are responsible for, like, if you're running in compatibility mode on a system or something. So you have, like, kind of old legacy 32-bit code on a 64-bit system. That's where those come into play. And then, like I said, you can use this RDMSR instruction to read them and inspect them to see what they should normally look like. So what will end up happening is what I have on this slide. So you see we have this ZW create file, which if you're familiar with Windows in user space, it's the same thing as nt create file, which I showed in the last slide. If you look at that exported function that corresponds to the create file call, you can see that that's it. That's 3 instructions, and that's how mostly every export from ntdll looks, right? So we load a syscall number, which is that hex 52 that goes into EAX, and then we issue the syscall instruction. Then when the processor sees that instruction, it goes and it reads from C000082. It finds whatever handler is responsible for running that syscall, and it goes and transitions execution there. So it's, we're going to talk about this when we talk about how to kind of exploit these issues, but this is kind of like a direct transition. Like the CPU is just like, oh, I'm just in kernel mode now, right? Like I'm calling this function. So it's KI system call 64's job to do some of the, like, kind of spin up work to say what, the kernel has its own stack and its own kind of context and things like that. So that function is responsible for doing all of that, and then figuring out what OX52 means and what function it should actually go call to handle whatever the system call was. So I don't think it's too much of a plot twist if you've been following the breadcrumbs in the rest of the slide, but the issue that we're talking about for this presentation is that essentially any accessed MSRs is all done. You need to be running in ring 0. So you need to be running in kernel mode to be able to execute the actual assembly instructions that correspond with that RDMSR and WRMSR commanded WinDebug. So the issue is basically, I don't know if it's people didn't understand what the impact was. We'll talk about that in a second. But the issue is we have a bunch of these device drivers that expose this instruction just willy-nilly, right? So if you think, like I said, a lot of this comes into play with, like, overclocking software, because you could tweak voltages and things like that using one of these MSRs. So what it looks like on the back end is you have this binary running in ring 0, and on the slide here I've shown sort of a subset of the command handler for that device IO control function, and you can see that we just kind of, whatever you pass in, they just call arbitrary MSR writes, arbitrary MSR reads. You can kind of set any MSR to anything that you want, right? So once you do that, if you kind of combine that with what we talked about in the past couple slides, if they don't filter the MSR access, then you can basically overwrite the system call handler, and then now that's how you get a ring 0 execution. So once you execute a system call, it goes to your overwritten callback function instead of whatever the OS kind of has pre-canned to do. So in terms of impact, we're going to do a couple slides in terms of like what I think sort of the severity of this is, but this issue or this bug was found, we found it in 20 drivers. It's probably in more. In a lot of cases, it looked like the code was almost reused. So that either tells me it's coming from like a standard library somewhere, or people just didn't consider it a security issue, so they just went ahead and did it, right? So in a lot of cases, this is in like overclocking software or like device management stuff that you would get from like a laptop vendor. So some of it came pre-installed, some of it, some of it like it was from like sort of big name hardware people. I'm not going to talk about specific bugs here to call anybody out, but in a lot of cases, if you went by sort of just like the amount of work we had to do to translate from one bug to the next, it was just, there was no filter, all the input was always the same, so we kind of had this implementation where it was like, I could run one exploit, and just by changing the name of the driver that I was talking to and one of those numbers that we talked about, it would work exactly the same across sort of all of these devices. So at a glance, so like I said, 20 plus drivers. If you went by download numbers, we're talking hundreds of millions of devices. Some of them were default installed on, like I said, they would be device management software with your hardware when you bought a new laptop or whatever. Out of the 20 that we're talking about today, 14 of them use the exact same format. So that's what I was talking about before. So I change what device I'm talking to, and I change whatever that special number is, but then my input is all the same. So you could just do a big switch case, and you could essentially own all of these drivers with like no additional effort, right? So one of the things that I'm going to talk about on the next slide is a lot of them, well, I guess half, right? Some of them required administrator access to kind of access these things. So it's super bad if they didn't do this, right? Because now you can have an unprivileged user just executing arbitrary ring zero code. About half of them had some kind of access control when you actually open the handle to talk to a device. But that was, that we're going to say, I'm going to say that's not sufficient. So that's the way it goes, right? And then one of them was fixed by the time I reported it. And another one tried to filter these MSR accesses, but their filter function had a different vulnerability in it, so you could still chain it together. So again, if we're talking about 20, you say 4 to 6 of them had some kind of extra effort put in. But like I said, the big punchline for us was it's the same code, it's the same bug, it's the same exploit, and you could just blast it to all these hardware vendors, and it would all work, easy peasy. So to kind of drive that home, this is our structures that we used for when we're actually exploiting the bug. So at the top of the slide, you'll see these are the sort of the data formats that all of these device drivers accepted. So we use these across like every exploit that we did. And so because the bug was so similar, and like I said, either a library or people just didn't think it was an issue, we could just reuse this across every driver. So in terms of like an exploitation thing, like this is pretty good, right? Because it's just I have one function and it always gives me a ring zero callback. And then the second half of this presentation is sort of all of the difficulties that go along with actually exploiting it. But the bug triggering half of it is super easy, right? So this is our input data, and that write MSR function is the one that overwrites for all of these drivers. So like I said, I'm just going to click through these really quick. Like I said, the exposure tended to be overclocking software, device management stuff. There's some other stuff like firmware, kind of low-level hardware interactions. Like all of those were vulnerable to the same issues and the same kinds of problems. In terms of administrator access, this is the only time I'm going to soapbox for this talk, right? But multiple vendors, when we reported them, said, well, it is bad, but you can't talk to our device if you're not already an administrator. And kind of the pre-canned line is, well, if you're an administrator, you can do whatever you want, right? Like you can reboot the system, you can turn off our security product, or whatever it is. So I don't want to say they were resistant, but they were like, isn't this kind of good enough? But from our perspective, like I said, we've already seen things like APT groups use signed drivers to avoid detection, or to have a ring zero callback, or to install a rootkit. you have all this kind of exposed like surface where, in my mind, if I was a defender or I was a system administrator, there's a pretty big difference between I have admin, so I turned your security product off and rebooted your system, versus I have admin and I can silently install my rootkit and you won't see any alerts. Because like I said, the big punchline is once you're in ring 0, you're at parity with all security products in the system, which means you can avoid them because it's kind of like a rat race in a way, right? But attackers always win that battle when you're on equal ground. So that happened quite a few times, and kind of our sort of summary is that security boundaries when you're going from user mode to ring 0 or whatever, it's kind of weird on Windows, because officially you need to have a code signature to like load a driver on modern Windows systems, but a lot of people don't consider that a security boundary for whatever reason. And I think that's one of the things, it's one of the takeaways where we kind of have to update how we think about these issues. Because if you're looking to defend from sophisticated attackers, things like signed driver loads that are being exploited they're not super common in terms of an attack toolkit or a chain or whatever, but if they do happen, like I said, they can kind of silently avoid all of your products, and then you're super hosed. So yeah, basically the punchline for this slide is Microsoft doesn't really consider admin a system a security boundary, but in sort of the modern landscape that we live in, I don't think it's probably sufficient, right? So I'm going to go over, so far I've talked about the bug, what it means, how you communicate with the device driver, how you trigger it. I want to go over sort of the workflow that we use to actually exploit this, because, well, I mean, one, I feel like a lot of places will just say like, oh, this bug gives you an arbitrary right, and you can use that to do remote code execution or whatever. So I wanted to walk through sort of a baby's first how to do device driver exploitation. So if you have one of these bugs, you can kind of understand mechanically what you need to do. And then also what you'll see when I go through these slides is kind of our thought process, because every Windows version added a little bit of trouble or pain or whatever. So how do we tweak our payload across stuff to kind of make sure we were running on any OS? Because like I said, the device driver, like that's where the bug is, right? So you're not tied to Windows 7 or Windows 10 or whatever. But when you're running on those operating systems, you have kind of extra work you need to do. So I'm a little, not short for this half, but I'll go relatively quickly, so feel free to yell out questions or we can talk after or whatever. But basically, when you have a privask bug on Windows, unsurprised, like many exploits, you'll use shellcode, right? The kernel shellcode that you're going to write is a little different if you've ever done like an RCE bug or anything like that. There's some things that are easier to do for an LPE, and there's some things that are harder to do. Most bugs that you see out there that are LPEs, the shellcode tends to do something like a token swap, or to give you system privileges or whatever. What we're going to talk about is that's fine, but again, if we're emulating like a sophisticated attacker, we probably want to do something kind of more involved, right? So for this next couple slides, the payload that we're writing is something that's capable of like reflectively loading a rootkit binary. So you'll be able to do whatever you want once you're in ring 0. And what that means from a practical perspective is when you're running a bigger payload, you also run into more stability issues, just for various reasons. So that's why we're kind of doing a deep dive in terms of like, well, this happens, we need to do this, and how do we craft our payload to say like 99.99% accuracy or whatever. So that's kind of what this slide is saying. But these next couple bullets are all of the things that we need to worry about when we're going and we're saying, hey, we can trigger it on Windows 7 and it's really easy. But what we found was as new versions kept coming out, we kept bumping up into like slightly different stuff. And it was never a direct mitigation for our vulnerabilities, but it made our payloads like a lot harder to kind of write. So I'm going to walk through each step in the next couple slides. Most POCs, like I said, most POCs are going to stop at token swaps. So again, just to drive it home, if you've ever written one of these exploits, like a token swap is a super easy payload to write. Like it's only, it's not that many in terms of like size or assembly instructions or whatever. When we're exploiting these bugs in particular, if you remember what I said was Once you do the syscall instruction, you're automatically in ring 0, but ring 0 is not the same thing as you're running in kernel space, right? Because normally the system call handler has to do all of the stuff to handle the transition from user to kernel mode. And because this primitive is kind of weird, we're executing in ring 0, but we're not, like, we have to handle a lot of that work ourselves, basically. So in addition to having our kind of, whatever our final payload is, we also have to make sure that, you know, we don't go too crazy, because if we don't handle the transition in kind of the same way that the operating system expects, one of the other sort of, not gotchas, but one of the other extra spicy pieces of LPEs, right, is if you mess up, the whole system goes down, right? So how do we handle all of that, and how do we be stable? So for Windows 7, it's a relatively straightforward process. Once you've done what we've already talked about and you overwrite the system call handler, you basically just, that's it. Like, you're done. You kind of, like, the only thing you really have to worry about is the transition that I was just talking about. So we kind of have to emulate what the OS would normally do in user mode to kernel mode. So from that, the other thing that we have to worry about is MSRs are shared per processor for the whole system, right? So, you know, in like legacy rootkits or whatever, that would be a place where you could hook to say, I'll install my own system call handler, because what that means is, like, system calls are responsible for basically any I/O or any low-level operation on the system. So they're kind of like a one-stop shop from an analysis perspective, because every application, every time they read a file, write a file, or whatever, it all calls the same function, all goes through the same mechanism. So what this means is, when our payload is running, we need to take some time and care to say, between the point where we overwrite the MSR and where our payload actually runs, anybody that makes a system call in the middle will call our function and will potentially crash, right? And there's kind of payload things that you could do to address that, but we're going to talk about sort of another way to massage our execution to make sure we don't, like I said, brick the whole system. And then, so that's kind of on the way in. And then we also have this problem of, if I'm handling the transition on the way into the kernel, how do I get out without, again, crashing or confusing the system in terms of like where we've been. And then where do we put our code, we're going to talk about in a second. So another problem that happens is, if you remember, or not if you remember, but I just said that system calls are shared for the whole system, right? So when I'm exploiting this vulnerability, I'm in like one process, and I send the request to the driver, and the driver overwrites the function pointer with whatever I tell it to, right? One of the sort of consequences of that is I need to stay running, because the only kind of data that I have control over when I do the overwrite is memory that's local to my process. So it's a little different from like a Win32k bug, where you're controlling the whole transaction and you're messing with like a particular object. Because in this case, like I said, they're shared system-wide, but I need to allocate memory in user mode that has my payload in it. So there's sort of a extra work that needs to go into making sure like you stay running while your exploit's kind of in progress. And for us, basically what this comes down to is, when you issue an ioctl, Windows has, or most operating systems, they have an idea of like process context. So on Windows, your process context is, if you're in ring 0, what handles and what virtual memory is valid, right? So if I'm in normal kernel space and I'm allocating kernel memory, that's kind of shared for all device drivers and the OS and everything else that's running there. But for user mode stuff, virtual memory is basically there to kind of divide up access to physical resources, right? So the virtual memory mapping for calc.exe is totally different from notepad.exe. So every address could be the same, it could be different, it could be invalid or whatever. But we need to put our payload in virtual memory, so we can only kind of execute the full kind of attack for this exploit in the context of our process, because we're running in user mode. So what that means is, from a stability perspective, if we get switched off, so we get context switched and another process executes, that thing that we put into the system call handler is not valid anymore. So if somebody, again, makes a system call, they're going to get some random unmapped user address, and we're probably almost certainly going to crash, right? And then, like I said, so all of these issues we have to deal with in our payload. So we need to make sure, one, our actual exploit is super small in terms of the code that we're using to trigger it, but then we also need to see if we can massage kind of the execution state to make sure like we're probably going to stay running throughout the whole thing. And we'll talk about kind of how I did this, but like this is true across all OS versions, right? So there's a bunch of kind of exploit mitigations that we run into later, but this is always the case because virtual memory is kind of more or less the same, right? So all of these things can all happen while we're running. So we can get paged out, we can get switched off. The memory could be, or sorry, the memory could be paged out, or we could be switched off, or something else could just happen to make a system call on that processor while we're running. So there's a bunch of kind of edge cases that we need to deal with, and it kind of, if it does crash in this context because we're not fully in kernel mode, it's kind of a pain to debug. It's kind of the punchline there. So the first problem we need to address is how do I get in and out of kernel mode similar to what the OS would actually do. And in this case, if you remember, I said ki system call 64 is the function that's usually occupying that MSR sort of address. So we can kind of consult that to say, this is the first part of our payload. So in our case, swap.gs, if you're not familiar with what this does, it doesn't really matter, but like this is a control register thing that lets the kernel know, oh, when you're accessing things like where the PEB would be in user mode, it's kind of a different mapping in kernel mode. So the first part of our payload is basically going to copy code from here to say, like, how much do I need to do to make sure? So the first couple instructions, swap.gs, which is like the kernel mode switch. And then you can see it does some stuff with RSP, so it's essentially preserving the user mode stack and swapping to a kernel mode. Because remember, kernel mode has their own view of data. They have their own stacks and things like that because you don't want kind of user mode callers to collaborate. Then similarly, when I'm getting out, you'll see that swap.gs instruction again, and then we do a sysretq, which you can read the Intel manual, but it's basically to return between modes. So we kind of have this sandwich situation. So we have the minimum amount of transition into kernel mode, and we have the minimum amount of transition out. And we're saying minimum because, again, we have to worry about all these sort of considerations of what happens if we get switched off and we crash the system or whatever. So how do we address the issue where we might get paged out or somebody might do a system call while we're running or whatever it is? So in this case, there's 3 user mode APIs that we can use to kind of influence the execution state while our payload is running, and essentially try to trick the scheduler to be like, no, like I'm really important right now, kind of thing. So set thread priority does exactly what you might think. You can say my thread is very important. Please do not schedule me off. Set processor affinity. If you remember a couple slides ago, I said MSRs are shared per processor. So we can say, I'm going to overwrite MSR on processor 2, only keep me running on processor 2, right? Because that's almost like the opposite problem if we get switched between processors where like we'll do a system call thinking we had it overwritten and then like it just works, right? And then sleep is kind of this is more of, I don't want to call it a trick, but it's more of a indirect mechanism. But if we sleep right before we call our payloads, what that tells like schedulers is, oh, this guy hasn't really run for a while, so I'm gonna sort of deprioritize switching him off because he already had his kind of wait period. But that's like an OS thing that I'm not gonna really go into here. So this slide's just an explanation of what I just said. Then when we're talking about how to do the transition, the good news is almost every register is preserved when we do a system call. So when I'm writing my actual payload, if I write it in raw assembly versus kind of regular C code to trigger the bug, then I can say, oh, RDX is always going to have a pointer to this or that or whatever it is. So I can kind of, I have a lot of control, which, if you're familiar with binary exploitation, like that's a super important kind of primitive to use when you're writing payloads because it gives you flexibility in what you could do with things like ROP gadgets or whatever. And then, the transitioning in and out, I don't want to keep hammering on that, but basically, like I said, we need to emulate what that ki system call function does. So we sort of are pretending to be a valid system call, which again, for Windows 7 is super easy because basically we just have our assembly blob, that's our payload. We call this swap.gs instruction, we call sysretq at the end, and then we're good to go. So this is that sandwich situation I was talking about. So whatever your kernel shellcode would be, which again could be token swaps, or in our case, we're talking about kind of a bigger chunk. You have the swap.gs and whatever stack setup is necessary. You run your payload, then you just kind of exit out as if you were a normal system call, and you're all good to go. There's some stuff that happens kind of mechanically that we can talk about after this that can mess you up if your payload does certain things, but that's just kind of a gotcha for your reference. So Windows 7 is super old. I don't know if you guys know. It's actually it's almost dead, right? Well, theoretically. So in Windows 8, they added something, or they started supporting this processor feature called SMEP on Windows. So what SMEP means is stands for Supervisor Mode Execution Protection. And basically what it means is in the scenario we're talking about, where I have code allocated in user space, that code cannot be executed from a kernel context. So what will happen is if we kind of run it like I just described, I do my system call, I get the function callback, no problem. But then the box will still crash and blue screen because now it's saying the processor's in kernel mode, but I'm executing a user mode address. So the way to get around SMEP is the same way you get around DEP, which is good. They rhyme, so it's kind of an easy way to keep track, right? But in DEP, you use something called return-oriented programming, or ROP, where you're reusing existing pieces of code. And that's kind of what we're going to do here. So we can't execute our user mode payload directly in a SMEP scenario. But what we can do is instead of pointing that MSR at like a random user mode buffer, we can point it at existing pieces of kernel code. And because we have all of this control that I was talking about with those registers, we're going to reuse those pieces to basically either copy our code into kernel space before we execute it, or we can turn SMEP off in the actual processor. So this is one of the situations it's a lot easier from an LPE. If you've ever written a remote exploit, one of the problems is always like, well, ASLR is usually on, so you need some kind of memory read primitive to figure out like where your stuff is. For LPEs, it's actually super easy because you can just ask, and the OS will just tell you where the kernel is. So that's one of the like helpful things on Windows. So mechanically, that's using this API called enum device drivers, and that just gives you a big list of all the drivers that are loaded, and it'll say NTOS kernel is here, Win32K is here, and then you can scan those to find your ROP gadgets and kind of build them dynamically. And then, so the full kind of workflow that you would use, so you would load library if you're on, that's kind of how you load and unload DLLs, but it's really just any kind of PE file. So you load library in user space, you know where it is in user space, then you can ask where it is in kernel space, you can just calculate the difference, and that's how you would find your ROP gadgets dynamically. So how do we turn SMEP off? There's a couple ways to do it. We could copy our code from user space to kernel space, because that won't trigger the SMEP thing that says you're running sort of unmapped code. It's a little easier and a little faster to just turn SMEP off for the whole system. So this is actually the thing that I mentioned like a video game driver was doing a little while ago, is they ran into the same issue where they had some kind of callback that was doing some kind of integrity check, and they kept crashing because of SMEP, so they would just turn it off. So SMEP is controlled by CR4, which is like another special register on the processor. Again, you can only access this from kernel space, but since we're running a kernel payload, we can build a ROP chain to toggle the appropriate bit off in this special processor and execute our code that way. I'm not going to go over this for time, but basically, like I said, CR4 is faster. If you want to do the copy from user mode to kernel mode, like allocating kernel mode memory can potentially be a big operation depending on how big your payload is. So there's a lot of extra concerns. So one of the other problems we have is, if you remember, I said one of the first things that we need to do is we need to look like kernel mode on the way in and on the way out. Now that we're ROPing, we're using pre-canned code. So like we need to find a proper gadget that will execute that swap.js instruction that we were talking about. And unfortunately, there is no swap.js ret. So if you're familiar with ROPing, like usually it's like one or two instructions followed by a return. So you can kind of just chain little pieces of logic together. We don't have a good gadget for this. So the approach we ended up taking is you can search for other kinds of returns. And in this case, we found one that looks like this. So technically, if you look, so swap.js, we have our instruction, and iretq is a, it's usually used to return from interrupts versus like normal function calls, right? So in this case, the first gadget in our ROP chain is going to be this pseudo interrupt return thing. So the lesson here is that, again, it's a bunch of weird execution scenarios, but if you kind of tweak the box in terms of what you're looking at a little bit, you can find these extra options. So this also is consistent across versions, which is good for us. It's in some like arbitrary kind of return handler thing. And then the details at the bottom of the slide you can read after, but basically there's extra work that goes into actually using this instruction, because like return just says whatever's on the stack, I'm going to go there. This has some extra kind of information going along with it. The CR4 gadget's super easy. We can load it. We can toggle the appropriate bit in our ROP chain just by doing like an XOR type operation. So this one wasn't really like a problem for us. And then we built a payload that looks like this. So this is kind of our ROP chain. We still do our swap GS via that IREQ gadget. Then we modify CR4. Then we execute our kernel shellcode. Then once we're in kernel mode, we can manually put everything back the way it's supposed to be. And we still do the swap GS sysregq at the end. This is the last thing. So I have a couple minutes for Q&A, right? So I'm gonna dive into this a little bit, and we'll cut Q&A a little short. So another weird thing that happened with this bug is between the time where we found them and between the time when we talked about them, Meltdown and Spectre happened, right? So if you're not familiar with those, they were like hardcore like CPU problems where you could leak or influence kind of kernel mode stuff from user mode based on weaknesses in the actual hardware. So the way that Microsoft mitigated this is with something called kernel page table isolation, where basically they've changed kind of what memory was mapped when you do the transit. So like normally, or not normally, but on older systems, if I did like a device I/O control, once I was in kernel mode, those kernel mode pages were shared across every process. With kernel or KPTI, what ended up happening is they, instead of mapping all kernel addresses in a user mode context, they only have one page. And that page's job is to go and find like the real page table and load it, which normally doesn't matter, right? Even from an LPE, like usually you're exploiting Win32K and everything's already set up. But because we have this weird thing where we're not fully in kernel mode, what would happen is we could figure out where all of our ROP gadgets should be, but when we made the actual transition, we only had one page to work with. So it's kind of like a weird situation where KPTI was meant to clobber something like a totally different issue, but then it impacted our payload because we now have to figure out like, can I find where all of my actual intended ROP gadgets are? And this one was a little trickier to deal with because, again, you only have one page of code. But essentially, we need to search. So we can see if KPTI is on with a system call that I showed in the last slide. But when we are on a KPTI system, we only have this one page from this KVAS code thing actually mapped. So any ROPing that we're going to do, we need to be able to find a gadget in that page. So it's a lot worse. It basically undoes all the stuff that I just said was super easy, because now we don't have access to whatever kernel binary we need. We only have one page, right? And this is one of the ones that that differs per version that we're exploiting. But basically, the punchline, like what we need to do is we need to find the normal CR3. So if you're unfamiliar, CR3 is another special register that maintains all of the mappings for what memory addresses are valid and where they are in RAM. And normally, this page's job is to go ahead, find CR3 for like normal kernel mode, and then swap that in. So we kind of have to replicate the same thing in our payload. So getting a CR3 modification gadget is pretty easy, just because that's something that happens all the time, actually. So like when you do a system call, the kernel has to say, like, here's all the memory that's valid in kernel mode. So this KI kernel exit is the gadget we use here. Like you can see, it's pretty short, so it doesn't impact our ROP chain too much. On 1809, it changed. It got a lot bigger. It got a lot harder. And you can see one of the weird things is that in the middle of this chain, there's another WR MSR instruction. So we're overwriting an MSR as part of our ROP chain. But one of the cool things about these bugs is they usually let you read arbitrary MSRs, just like writing them. So we can build our ROP chain to basically put the right value back there. So that's the kernel mode piece of it. I want to give shout outs where shout outs are due, right? So we still have a problem of we need to figure out what the right value for CR3 is. And in this case, we consulted, so Ionesco did a talk a couple years ago about how you leak this. So we reused his technique to basically use WMI to leak what the actual system call thing, or what the right CR3 value is supposed to be. Then we can preload that into our ROP chain and kind of build it dynamically that way. So when we run these gadgets, our payload doesn't mess everything up. So the full chain, right, is we ROP to that swap GS IREQ, because that gadget's still there. We do this weird CR3 modification thing, so we kind of have to build our stack to handle sort of all of these weird situations, but we can read the MSR value, which is the big kind of gotcha for us. And then from there, we ROP to a CR4 modification gadget to turn SMEP off. So easy peasy, right? Is the clicker still on? Oh, there we go. Okay, weird. So this is kind of the full view of our payload. And like I said, there was a lot of kind of nitty-gritty technical details, but the punchline is like, it was a weird situation where we were running into different kernel mitigations. We were running into stuff that wasn't intended to break our payload, but it was breaking our payload. And then on top of that, we also had to make sure we were handling cases where like we didn't want to get switched off and we didn't want to crash the system because we weren't running kind of fast enough sort of thing. Then in user mode, we handle some of the scheduling stuff with as much kind of luck as we can. And we use this CR3 leak to build the full ROP chain. So this is the kind of ROP chain that we would do on 1809, which is like the newest version that we tested on. So most of this we've already talked to, so I'm going to kind of wind down. Then the last consideration is where we actually put the ROP chain. So similar to our payload problem, we are allocating memory and executing it from user mode, but you still have all the same problems that I just described of like, what if our user mode ROP chain gets paged out, or what if we get switched off and the user it's not validated. So you have the same problem, but it's worse in ROPing because like you have less control over what's actually happening on the system. For us, kind of the easy mode is you can allocate a user mode stack and then call a virtual lock API to kind of make sure your memory is always resident while you're executing. And there's some other way you can go pretty crazy in terms of the actual ROP chain allocation stuff. Like the kind of correct way to do it would be to like leak a kernel address and then spray the stack in kernel mode and then ROP there. But that usually wasn't that different. So I mean, again, it's kind of when you're writing these payloads, you need to make sure you don't go too hard if you don't have to, because we already have a lot of weird stuff to deal with. So like, it doesn't behoove us to add extra exploitation problems. And then I'm not going to really talk about mitigations because I'm not a defense guy. So, but basically, on like newer systems with Hyper-V, they'll block the MSR access. Theoretically, Microsoft could also add some kind of like cookie check when you're doing the syscall transition stuff, but I mean, they're not going to do that, so that's fine. And then the CR3 leak already works. So I had a demo. I guess it'll be in the slides when they get uploaded. But it just walks you through each step of our payload in terms of like what we did here, where did we put our code, and things like that. So I was only a little over, but I can do questions or Q&A now.